In this lesson, we're going to review the 6 basic trigonometric ratios, and they are developed from the right triangle. So before we write them all down, we're first going to define the 3 sides of the right triangle. As always, opposite the 90-degree angle, this is going to be the hypotenuse. And it's always the longest side of the triangle. And then depending on the angle we are referencing, if I have my theta right here in this corner, then the adjacent side is going to be the side that creates the angle. So the angle we're dealing with is always created between the hypotenuse and the adjacent side. And then across from the angle, that's going to be the opposite side. So using this notation, we can define the 6 trigonometric ratios. Now the ratios are created because anytime you have a right triangle, dependent on the angle, the ratios of the sides are going to be constant, because every right triangle that has this specific angle measure as one of its angles is going to be similar to every other right triangle with those same angle measurements. So the ratios of the sides, because of what we know of similar triangles, those ratios are going to be constant, which is why before calculators we had huge tables of values for all the different trig ratios, because for every single angle measurement we have a locked-in value for sine, cosine, tangent, and their reciprocal identities. So we're going to write all those down right now just as a quick review, because you can never do too much with this trig stuff. It shows up over and over and over again. So we'll start with our 3 basic trig ratios: the sine, the cosine, and the tangent. And here's how they are defined. The sine is defined as the opposite over hypotenuse. So we can shorten that, opposite over hypotenuse. The cosine is adjacent over hypotenuse. And the tangent is always opposite over adjacent. And again, for every angle measure, for every right triangle, depending on the angle measure, these ratios don't change. Now, to obtain the next 3, they are just the reciprocal of the original sine, cosine, and tangent. So the reciprocal of the sine is the cosecant. So instead of opposite over hypotenuse, it's going to be hypotenuse over opposite. The reciprocal of cosine is secant, so that's hypotenuse over adjacent. And the reciprocal of tangent is cotangent, that's adjacent over opposite. There's one more that you should be aware of, and we're going to bring it up later, but it's very important. It shows up quite a bit, and that is another way to represent the tangent of theta. And I'll talk about this in more detail, I think, in a few lessons coming down. The tangent of theta is, if you look at opposite over adjacent, it can also be sine over cosine. Because if you take the ratio of sine, if you think about it, sine is opposite over hypotenuse, cosine is adjacent over hypotenuse. So if you simplified that complex fraction, opposite over hypotenuse over adjacent over hypotenuse, well, what happens? The hypotenuse reduces down and you're left with opposite over adjacent, which means tangent is also equal to sine over cosine. So that's going to be very useful coming up. And these are your 6 basic trig functions. It's important that you memorize how they are defined, because you're going to be relying on them quite a bit. So here's a basic example of how we would find all these ratios. If sine of beta is 3 over 7, we're assuming this is it's just defined as 3 over 7. Find the 5 other ratios and leave your answers exact. That means if I end up with a square root, I don't want a bunch of decimals. I leave it as a square root, preferably simplified, but we leave it as a square root. So, sine of beta, that implies a right triangle, and I don't really care what angle measure beta is. I'll put them in here, because what I know is the sine of beta is 3 over 7, which means the opposite side is going to be 3, and the hypotenuse is going to be 7. So if I'm going to find the 5 other ratios, I got to figure out the adjacent side. Well, when you have a problem like this, Basically, when you have two sides, you need to find the third side. We don't need to use any trig. We're just going to use the Pythagorean theorem to do this. So he's also handy. Okay, remember that's a squared plus b squared is equal to the hypotenuse squared. So we do a little mini formula here, and 3 squared plus b squared is equal to 7 squared. We get 9, and that's equal to 49. So b squared is 40, which means b is going to be the square root of 40, or 2 radical 10. So now I can put that in. If it'll let me erase. If not, I'll just write it in here. 2 radical 10, although I don't like that 2. Hold on. 2 radical 10 is the other side. Once you have that, you can just write down all your ratios. So I can, let's see if I have room for them all here. Alright, I'm going to list the other 5 down here, because once I have my triangle, then you just pull them off. One other thing before, because we haven't gotten into angles around the circle yet, so if I give you a problem like this, we're going to assume everything is positive, because we're dealing with a basic right triangle. So the cosine of beta is going to be 2 radical 10 over 7, and we can just write all these in. 2 radical 10 over 7. Tangent is opposite over adjacent. Now, when you have that, I would expect you to rationalize. So you multiply top and bottom by radical 10, and you get 3 radical 10 over 20, it looks like. So cosecant is the reciprocal of sine. If sine is 3 over 7, then cosecant is 7 over 3. The secant is going to be 7 over 2 radical 10. I don't quite have room to rationalize that, but that's going to be 7 radical 10 over 20. And then the cotangent is going to be 2 radical 10 over 3. So those are pretty easy to get once you get your original triangle. Alright, there are 2 special triangles that we deal with, and it's really important that you memorize or you are able to very quickly draw these triangles, because you're going to have to memorize or understand how to get all the trig ratios for these special angles. The first one is the 45 right triangle. So we have a right triangle with a 45-degree angle, which makes the other angle also 45. Since it's 45 and 45, if one set leg is 1, the other one is 1, because their legs are equal. And if I would do Pythagorean theorem on this, the hypotenuse ends up being radical 2. So it's a 1, 1, radical 2, which means for 45 degrees, if I use that triangle, I can find the exact value of the cosine of 45 degrees, and the sine of 45 degrees, and the tangent of 45 degrees. I can also find the value for the 3 reciprocal functions, but once I find cosine, sine, and tangent, it's pretty elementary to do the reciprocal functions, which we are going to do in a big table when we get to class. So let's just start with the basics here. Cosine of 45 is 1 over radical 2, but we don't like to leave it like that, okay, because we don't like radicals in the denominator, so we typically know the exact value of cosine of 45 degrees as radical 2 over 2. Sine is the same way. It's going to be radical 2 over 2, and then the tangent of 45 degrees is basically 1 over 1, so the tangent of 45 is 1. Now the second special triangle is called the 30-60 right triangle. And here's how this was developed for me when I was in school, and I've never forgotten it, so it's kind of helpful. If I start with an equilateral triangle has the same length on all sides, and we know each angle is 60 degrees. Well, I'm going to make that side length a side length of 2. And here's what we're going to do. We are going to create an altitude in this equilateral triangle. So what that does for us, my original angle up here was 60 degrees, but an altitude in an equilateral triangle acts as an angle bisector. Therefore, on one side, this now has an angle of 30 degrees, and here's my right angle down at the bottom. Here's what else it does. My original length was 2, but an altitude in an equilateral triangle bisects the opposite side, So instead of a length of 2, if I took just half the triangle, I have a length of 1. That's how our 30-60 right triangle is created. It's basically taking an equilateral and chopping it in half from the altitude. So the 60 degrees was the original vertex of an equilateral triangle. He stays there. The 90 degrees is part of the altitude. The 30 is created by bisecting that top angle. My original side length was 2, and then the altitude bisects the bottom side, so that side is 1. Once you have this, you can get your ratios. So just remember that the hypotenuse is 2, and across from the 30 degrees is the 1. Now, if we did Pythagorean theorem on this, I'd have to find the other side. So 1 squared plus this squared is equal to 4 squared, and when you solve it, you end up with radical 3. So this is the 2, 1 radical 3. And you have to remember the radical 3 is the altitude side. The 1 is across from the 30 because it's the side that was cut in half, and the 2 is the original length. So now we can write down our trig ratios. The cosine of, actually I'm going to have 2 columns here. We're going to do the 30 degrees and the 60 degrees. So the cosine of 60 degrees is going to be, if I look at this, it's going to be adjacent over hypotenuse. Cosine of 60 is 1/2. The sine of 60 is therefore radical 3 over 2. And the tangent of 60 is going to be radical 3 over 1, opposite over adjacent, so it's just radical 3. Now, what you should also know is that the cosine of 60 is going to be the same as the sine of 60's complement. So the cosine of 60 is also the sine of 30 degrees. So the sine of 30 is opposite over hypotenuse. That's exactly 1/2. The cosine of 30 is going to be radical 3 over 2. And the tangent of 30, if I look at this, I always have to think about my triangle when I do tangent, is 1 over radical 3. We don't like to leave it like that, so that's going to be radical 3 over 3. So you're going to have to memorize these ratios or draw the triangles pretty quickly. Here's how I always start. I always know that the sine of 30 is exactly 1/2, and there's a little video I'm probably going to show you in class to try to help you remember that. The sine of 30 is always exactly 1/2, which means the cosine of 30 is radical 3 over 2, and then they switch spots for 60 degrees. It's not too bad to memorize these things. So in class we'll do that, and we'll complete a big table to have all of our special angles in the table. And then just one more thing to note, if you have sine, cosine, and tangent, you can just use the reciprocals to obtain secant, cosecant, and cotangent. So if I have, let's say, the cosine of 60 degrees is 1/2. Remember the sine of 60, we'll just do this quickly, is radical 3 over 2. And the tangent of 60 is going to be radical 3. So the secant of 60 degrees is the reciprocal of 1/2. It's going to be 2. The secant of, or the cosecant of 60 is going to be 2 radical 3 over 3, because we want to rationalize the denominator. The cosecant of 60 degrees is 2 over radical 3, or 2 radical 3 over 3 is how we like to write it. And then the cotangent of 60 degrees is the reciprocal of radical 3, which means the cotangent is radical 3 over 3. So once you have the original 3, you can use reciprocals to get the secant, cosecant, and cotangent. Finally, I want to remind you of the definition of the angle of elevation and the angle of depression. Those are surveyor's terms, and they show up a lot in application problems. Whether you're talking about elevation or depression, it's always being measured from the horizontal. So whether you're measuring from the horizontal looking up, so if this is my horizontal line, if you're measuring there and looking up, that's going to be angle of elevation. If you're measuring there and measuring down, it's going to be angle of depression. But what you have to remember is it really refers to the same angle. Because if I draw a triangle, and here I am, And if I'm looking at this, the angle of elevation would be right there. But if I wanted to state the angle of depression, it would be that angle up there. Since these are parallel lines and we have alternate interior angles, they're going to be the same angle measurement. So whether you're talking about the angle of elevation or the angle of depression, it's still referencing the same angle measurement. And you have to remember that when you draw your diagram. If you have angle of depression, you can put that same angle down here and treat it like angle of elevation. So we will work some examples in class, and we will fill out our table of exact values in class, and go from there with basic trig.